In this video, the topic related to R-2R ladder DAC, digital to analog converter. R-2R ladder digital to analog converter. Digital to analog converter. This is DAC. Diagram is here. Consider 3-bit R-2R digital to analog converter. We use a binary adder network. Consider binary adder network here. R-2R R-2R. One more 2R is connected to ground potential. Here the value, here these are the switches like that. These switches are connected either 0 or 1 depending on the data input, binary input to the 3-bit R-2R digital to R-2R ladder digital to analog converter. The switch movement is direction in this way. Here we use positive reference voltage. This R-2R ladder is connected to half amp. Half amp is in inverting configuration. This one is output is V0. 2R. This one D1, D2 and D3. The switches are moving in this direction or in this direction. Depending on the input data, that is data watts. This one is a D2, D1, D2, D3. VR like that. This one is a MSB. This one is LSB. In case of wide range of resistors are required in a binary weighted resistor type digital to analog converter. Wide range of resistors are required in binary weighted resistor type digital to analog converter. The values of resistors are 2R 2 power 1 or 2 square or 2 cube r and so on and so forth, 2 power n into r. That is the drawback of the weighted resistor type, binary weighted resistor type digital to analog converter. This can be avoided by using R-2R ladder type digital to analog converter, where only 2 values of resistors are required. This can be avoided. This can be avoided by using R-2R ladder type digital to analog converter, where only 2 values of resistors are required. 2 values of resistors are required. This one is ladder network, R-2R ladder network, R-2R, R-2R, like that. Last section to last one 2R is connected to ground. This one is 3-bit R-2R digital to analog converter. 3 bits means D1, D2, D3. This one is MSB. This one is LSB. It is well suited for integrated circuit realization. The typical values of R is range from 2.5 kilo ohms to 10 kilo ohms. The next important point here is it is well suited. It is well suited for integrated circuit realization. The typical value of R ranges from 2.5 kilo ohms to 10 kilo ohms. Here only R-2R resistors are used. R is below 1 kilo ohm. 2R means 2 kilo ohms. Need not required wide range of resistor values. In case of binary weighted resistor type digital to analog converter requires a wide range of resistor values. This one is a binary ladder network for digital to analog conversion. Just consider this one. R 2R, here 2R, this one is R, this one is 2R, one more 2R is required, that is connected to ground. Suppose D1, D2, D3. Here D1, D2, D3, all are ones. Suppose all are ones. Therefore, this switch is connected to these 3 switches are connected. That means D1, D2, D3 switches are connected to VR only. These 3 switches are connected to VR. That is, this one is VR reference voltage here, because D1, D2, D3 is equal to 1. Here D1 is also there, D1, D3, here D3, D2, D1. This one is MSB, this one is LSB. MSB, this one is LSB. By using network analysis, simplify this ladder network configuration using Thevenin's theorem here, or nodal analysis, whatever it may be. This one is consider this portion 2R here, 2R, VR, this one is a D3, apply Thevenin's theorem here, D3 here, D3 into VR, Thevenin's theorem apply here, find out voltage, Thevenin's voltage, apply KV, apply nodal analysis to this node. The node voltage is here, this node and this node is same. The node voltage is VTH. To this node, two resistance values are connected, 1 by 2R plus 1 by 2R. These two are connected. Adjacent node voltage is adjacent node voltage is VR. D3 into VR. Suppose D3 is equal to 1 into VR. D3 into VR. D3 into VR by resistance is 2R is equal to 0. At this point, the voltage is VTH. Apply nodal analysis. VTH into the consider the conductance or admittances which are connected to this node are 1 by 2R plus 1 by 2R. Adjacent node voltage is D3 into VR. That means minus here, minus sign, minus D3 into VR by 2R. Therefore, VTH is equal to 2 by 2R is equal to D3 into VR by 2R. 2R, 2 is cancelled, R is cancelled. Therefore, VTH is equal to D3 into VR by 2. D3 into VR by 2. This is the VTH. Next, find out equivalent resistance, Thevenin's equivalent resistance. In order to calculate Thevenin's equivalent resistance, VR is 0. Put VR is 0. That means D3 into VR is 0. Here 2R. Both are connected to ground. Find out RTH, Thevenin's resistance. RTH is equal to 2R into 2R by 2R plus 2R. That is equal to 4R square by 4R. That is equal to R. Therefore, the entire portion of the network is simplified as a voltage source in series with the resistance. That is VTH. That is VTH in series with some VTH value. That is VTH representation is like that. VTH in series with some resistance R. Consider this one up to this point here. Up to this point is here is a VTH in series with some resistance R. Simplified network like that. This simplified network is connected to the remaining portion. Therefore, the circuit, simplified circuit again. This one is R. This one is R. D2. This one is D2 into VR. Here D2 VR. Suppose D2 is equal to 0, R is directly connected to ground. D2 is equal to 1, that means VR. VR is connected to R. D2 into VR. This one is VTH. VTH is D3 VR by 2. Put in the box. Again apply node Thevenin's theorem here. Let it be VTH1. VTH1. Here the node voltage is VTH1. Here the node voltage is VTH. Apply nodal analysis at this point VTH1. Apply nodal analysis. VTH1 is equal to what are the admittances which are connected to this one is 2R. This one is 2R. To this point, the resistors connected are 2R, R plus R, 2R. R plus R, 2R. Consider admittances, that means 1 by VTH1 into that node voltage VTH1 into 1 by 2R plus 1 by 2R. Adjacent node voltage is here is minus, here minus, plus minus. Suppose here minus plus means plus VTH by 2R. Here minus sign is there, minus VTH by 2R. Here another voltage source is there, that is minus D2 VR by 2R is equal to 0. Find out VTH1. VTH1 into 2 by 2R is equal to VTH by 2R plus D2 into VR by 2R. D2 into VR by 2R. 2 to cancel, that is R is cancelled. Therefore, VTH1 is equal to VTH by 2 plus D2 into VR by 2. D2 into VR by 2. In order to calculate, this is the VTH2, VTH1. This one is VTH1. Put in the box like that. Next, calculate equivalent resistance. In order to calculate equivalent resistance, these two are VTH and D2VR is short circuited, and R is 2R. This is also 2R. 2R connected in parallel with 2R, therefore RTH1. RTH1, that is 2R connected in parallel with 2R. This one is RTH1. RTH1 is equal to 2R into 2R by 2R plus 2R, that is 4R, that is R. Therefore, VTH1 R, VTH1 R. Up to this one, the simplified diagram is VTH1 R. The remaining one is also connected here. R-2R D1 into VR. The remaining one is also connected to that VTH1 in series with R network. That is R-2R D1 into VR. D1 into VR. Now find out Thevenin's equivalent circuit, that is VTH2. VTH2. VTH2, apply nodal analysis at this point. VTH2 into the resistance connected are 2R, R plus R 2R. That is 1 by 2R plus 1 by 2R minus VTH1 by 2R minus VTH1 by 2R minus D1 VR by 2R is equal to 0. Simplify this one. Find out VTH2. VTH2 is VTH2 2 by 2R, VTH1 by 2R plus D1 VR by 2R. 2 cancel, R cancel. Therefore, VTH2 is equal to VTH1 by 2, VTH1 by 2 plus D1 VR by 2. D1 VR by 2. VTH1 is equal to VTH by 2. Later I will submit here. Okay. VTH2 is equal to VTH1 by 2 plus D1 VR by 2. VTH1 value is here. VTH1 value is VTH by 2 plus D2 into VR by 2. VTH1 value is VTH by 2 plus D2 VR by 2 by 2 plus D1 into VR by 2. That is equal to VTH by 2 into 2, 4. D2 VR by 4. D2 VR by 4 plus D1 VR by 2. This is the VTH2. Now substitute VTH also. VTH is equal to VTH is equal to D3 VR by 2. D3 VR by 2. VTH is equal to D3 VR by 2 into 4. D2 VR by 4. D1 VR by 2. Therefore, VTH2 is equal to D3 VR by 8 plus D2 VR by 4 plus D1 VR by 2. D1 VR by 2. This is the VTH2. Now calculate RTH2. RTH2 means VTH1 is short circuited. D1 VR is also short circuited. R plus R 2R is this is the 2R connected to ground. This is also 2R is connected to ground. Therefore, RTH2 is equal to 2R into 2R by 4R. 4 cancel. Therefore, RTH2 is equal to R. Therefore, the simplified diagram is VTH2 and R. VTH2 and R. This is the total circuit diagram where VTH2 is equal to D3 VR by 8 plus D2 VR by 4 plus D1 VR by 2. total ladder network. This is the, at this point, the simplified ladder network is like that. The simplified ladder network is VTH2 and R. VTH2 R. At this point, VTH2 R to VTH2 R. This one is R connected to this point. The simplified network is connected to this point. The op amp is in inverting configuration. Suppose non-inverting means the ladder network is connected to plus of that op amp. This one is inverting configuration. The ladder network is connected to inverting terminal of the op amp, that is minus terminal of the op amp. Minus terminal of the op amp. Therefore, the simplified network is connected to op amp. The simplified network is connected to op amp. Here VTH is equal to D3 VR by 8 plus D2 VR by 4 plus D1 VR by 2. D1 VR by 2. Finally, the simplified network is connected to op amp, and then find out analog output voltage, and then find out analog output voltage. This one is VTH2 R. This one is op amp. Minus plus is connected to this terminal. V0. This one is RF. Like this one is RF. Output voltage is V0. Here inverting configuration. Non-inverting terminal of op amp is connected to ground. Here VID is equal to 0. That means here 0 volts, here 0. Apply nodal analysis at this point here. 0 node voltage here, 0 into what are the resistance are connected to this 0 node? 1 by R. R is the resistance connected to this node. That consider admittance 1 by R plus 1 by RF. Minus adjacent node voltage is VTH2 by R. Minus adjacent node voltage to this 0 node voltage is minus V0 by RF is equal to 0. Therefore, VTH2 by R is equal to minus V0 by RF. Therefore, V0 is equal to minus RF by R into VTH2. V0 is equal to minus RF by R into VTH2. Minus RF by R. VTH2 is here D3 VR by 8, D2 VR by 4 plus D1 VR by 2. That is equal to D3 VR by 8 plus D2 VR by 4 plus D1 VR by 2. D1 VR by 2. That is equal to VR is the common term minus RF VR by R minus RF VR by R. That is equal to D3 by 8, D2 by 4 plus D1 by 2. This is the output voltage V0. V0 of the 3-bit digital to R-2R ladder DAC, digital to analog converter. This one is a 3-bit. Suppose 4-bit means we use D4, D3. For 4-bit, R2R ladder DAC, is V0 is equal to minus RF by R into VR. D4, DQ, 2 cube is 8, D4 by 16 plus D3 by 8 plus D2 by 4 plus D1 by 2. This is the for 4 bit. Maximum value is 2 per 3 bit. Here is 2 power n, that is 2 cube, that is 8. This one is 2 square, 4. This is 2 power 1. Here 2 power 4, 2 cube, 2 square, that is 2 power 1. For nth bit, this is 2 power n, 2 power n minus 1, 2 power n minus 2. This is 2 power n minus 3, and so on and so forth. Final output voltage V0 is equal to minus RF into VR by R dn, that is dn by 2 power n plus dn minus 1 by 2 power n minus 1. Suppose n is equal to 4, d4, 2 power 4, 4 minus 1, that is d3, 2, 4 minus 1, 2 cube, dn minus 2 by 2 power n minus 2, dn minus 3 by 2 power n minus 3, and so on like that. For n is equal to 3, d3 by 2 cube, d2 by 2 square, d for n is equal to 3, d1 by 2, 3 minus 2 is 1, like that. D power n minus 3 by 2 power n minus 3. This is the R-2R ladder. Here only 2 resistor values are used. Here are R and 2R values. In weighted resistor type digital analog converter and R-2R ladder type digital analog converter, current flowing in the resistor changes as input data changes. This is the main drawback. More power dissipation causes heating, which in turn creates non-linearity in digital to analog converters. This is a serious problem and can be avoided completely in the inverted R-2R ladder type digital to analog converter. This is the analysis of 3-bit R-2R digital to analog converter. Here we use a ladder type network, consists of R-2R resistor values. With this, the total analysis is completed.